how wide is that gap? 3 inches, yeah. So a 3-inch diameter object should be able to pass through it easily. But what if that object was magnetic and these were conductors? Then this magnet, the faster it went through, the stronger a magnetic field it would induce in each of these pieces. That one would become strongly red and that one would become strongly blue. For those of you who aren't entirely familiar with what I'm talking about there, this is just a very basic electrical principle called Lenz's law. So nothing controversial about it whatsoever, but some people do get very confused by it, even though it's quite simple. So I'll explain it in full a bit later on. So now the magnetic fields would extend outwards and make the gap appear significantly narrower and significantly deeper and rounder in profile. So effectively we've converted a thin slit into a much deeper slit, and a wide slit into a much narrower slit, and a square edged slit into a much rounder edged slit. We've made 3 significant changes. So now this magnet, as it goes through, inducing those fields in it, no longer sees that gap the width we see it. It sees it significantly smaller, thinner, longer and more rounded. The crux is that the slit is no longer the same width that we see it. It's a lot thinner, it's a lot deeper, more corridor-like and a lot rounder. So you can see why the magnet would start deflecting away from the edge before it even got there. This is just a very basic electrical principle called Lenz's law. Nothing controversial about it whatsoever. Because of the profile around it, the roundness, and why it would then start to deflect away from the other edge. And again, the opposite edge. In short, it would zigzag until it was going down a very narrow corridor down the middle of the slit. And then as it leaves, it would do the exact opposite. The polarities would be switched as it leaves, because that's what Lenz's law does. It pushes against pushes and pulls against pulls. So as it leaves, it would be drawn back behind the slit. It would be as if it was being tethered to the slit, trying to stop it from leaving. Imagine you're riding a bike, but somebody's tied one side of your handlebars with a thin piece of elastic to a lamppost. You're going in a straight line, but not for long. You find yourself getting pulled to one side, don't you? That's like diffraction, really, isn't it? That's what's going on here. Lenz law pullback effect, as I would call it, instead of the braking effect. It's all the same stuff. So it's as if the photon is fighting elastic bands attached to the material, because it's being pulled back towards the material that it's inducing current in. Displacement current, that is. Because even metals are dielectric at light frequencies. So this effectively works as a magnifying glass for the pattern that's already been created within the slit. It just spreads it out. And the narrower the slits, the more it spreads it out, because the less the photons passing through can avoid the proximity to the slit edge, which is what governs how much the pullback effect is. As if it was being tethered to stop it from leaving the slit, pulled behind the slit into its shadow, because that is Lenz's law. It pushes against pushes and pulls against pulls. It doesn't want it to leave. That's why we have diffraction. This is a good time to remember that that magnet you saw rolling back and forth there is bigger than it actually looks, magnetically speaking. That's why we have diffraction. So that's why we have zigzagging into the slit and why we end up with pattern because of exit corner shadowing. And that's also why we have diffraction, magnification, fanning out, because Lenz's law doesn't want the magnetic particles to escape. The thinner the slit, the less those particles can possibly escape diffraction. The wider the slit, the more they can escape it. So I'm basically saying that the minima are probably nothing more than shadows of the exit corners as seen by the various angles forced to zigzag through the slit. They don't fill in for one another because the axis keeps getting reset to the slit exit corners. So even though they swap sides and you would imagine cancel one another out, left and right just swap roles, that can't actually be happening because the axis keeps getting reset. So there's always a gap. And by the time the difference between the proper axis and the reset axis is so small that it should make no difference, by then we're way into the region where the minima have gone because of diffraction. Yet the minima have then gone simply because the diffraction effect happens more at light escaping at that angle because they remain under the influence, so to speak, of the Lenz law pullback effect for longer than those that are escaping, 12 o'clock type angle. The ones that are going more like 2 o'clock, etc., those can't escape the pullback effect for long, so that the width gets stretched.
Trying to represent diffraction, so I wanted to pull the glass plate down to see how it spreads the different angles. I'll confess these aren't actually, this isn't actually paint, it's toothpaste. Let's be honest, I don't have a lot more use for it. But it does actually kind of illustrate that rays in that direction hardly affect it at all, well not at all, but when there's a slight angle they are spread sideways, widthwise. Steeper angles even more widthwise, and steeper angles again even more widthwise, to the point where if these ray angles were representing maxima and minima, the gaps being the minima, what was minima, you can appreciate that where the angles of rays are steeper, the diffraction, the pullback effect of Lenz's law, as I would argue, is causing the minima to disappear at the steeper angles, in other words, the outer fringes. The Lenz's law pullback effect is stretching the width of the rays that are at a steeper angle because they remain within the range of the surface. This is causing the diffraction for longer than these ones. Rays going that way, they escape the effect very quickly. Rays go in at a steeper angle, escape less quickly, and an even steeper angle even less quickly, till at a certain point, if you're virtually travelling parallel to the surface that's causing the diffraction, the Lenz law breaking effect, the Lenz law pullback effect in effect, if you're virtually travelling parallel to them, it takes you a much longer time to escape that effect because you're not getting away from it fast enough. So you're suffering the pullback effect for longer. Therefore, the rays are getting wider and stretched out. The minima eventually just disappear altogether. They get closed up. The space that were the minima gets taken up by the maxima. Now, it's only toothpaste, but it seems to work. I was quite surprised that I didn't think the demonstration would work.
But you must be thinking, how can any of this apply to insulators? This is all well and good if the slits were always made of metal, but more often than not they're made of insulators. It's basically because we're talking about alternating magnetism and hence alternating current. That's why alternating current can pass between the insulating layer inside this capacitor. The higher the frequency of alternating current applied to it, the easier it passes through. It doesn't even recognise that as an insulator. It's like putting a piece of paper in front of my face and saying you won't be able to hear me now. So you think, wasn't a fair example? That was a very thin sheet of paper, and the insulating layer in this capacitor is equally thin. It's one thing to apply a changing magnetic field, an alternating magnetic field, to a thick piece of conducting material, but Steve, why don't you try applying it to a thick piece of plastic material? Well, exactly the same thing happens, surprisingly. That's why you can use that thick piece of plastic material as a transmitting antenna and a receiving antenna. It works perfectly fine. I'll show you. Who would think you could transmit and receive between two glue sticks? Can't quite see the meter there, can you? Who would have thought you could transmit between two glue sticks? You wouldn't think you'd be able to use glue sticks as antennas, would you? But there you go. Oops, yeah, the alignment still works, but I'm only showing because there's always going to be somebody saying, yeah, that can't work. There's some silly excuse why. There's always going to be somebody saying, conductors conduct, insulators insulate. Well, it's a bit more complex than that. It's a bit more complex than that. I know people like to oversimplify everything. I can go quite far away, but I'm off camera. Anyway, that's just for the doubting Thomases who don't believe in displacement current or anything else. I was curious whether that would work. A long piece of wood transmit with that. Bit ridiculous, isn't it? I'll give it a go, you know. I can't get it all on camera, obviously. Put the camera further along there. You can just see the end of the glue stick receiver. Can't hold it steady. Bit weird, isn't it? Just if I make actual contact, I wonder what happens. Turn that up a little bit. I suppose what I'd like to try now is tried normal length glue sticks, yes. God, that's loud, isn't it? I'd like to try shorter lengths now, see what happens with shorter lengths. I'll halve the length of it. See, on its own, get very little. Put that in there right now. Okay, well that was great. So, tell you what then, I'm going to make a quarter. I'm going to quarter it now. Okay, so it's about a quarter length now. Just leaving that little flat bit there so it'll fit in the WR90 waveguide. Actually, this is WR62. I told you this isn't WR90. This actually does prefer a much higher frequency. It prefers 18 gigahertz, not 10. Here we go again. What form of energy it takes, I do not honestly know. So the photons radiating from the gun diode at 10,000 million times per second, 10 gigahertz. So the energy from the gun diode is travelling across one gap, two gaps, three gaps, 4 gaps, 5 gaps in effect, to make it to the receiver. All these things are insulators, and yet the energy is travelling from the transmitter to the receiver via insulators 1, 2, 3, 4 and 5. Yes, there are losses, but it's undeniable that we are receiving energy via several insulators, usually called dielectrics. a fancy term for insulators. Now, the plastic glue sticks, despite being really good insulators, were able to improve the transmission of energy from the transmitter to the receiver. We're able to channel it in a much more directional way than the air alone, where it was allowed to diffract, disperse over a wide area, get wasted, so very little was actually received. But with the plastic insulators in between, they worked as antennas, directing that energy. In effect, therefore, we cannot rely on our measuring instruments to judge the actual width of the slits as seen by magnetic particles going through those slits. So if light was a magnetic particle, it's not going to see the slit the width we think it is, it's not going to see it the depth we think it is, it's not going to even see it the shape we think it is. Therefore, the Lenz law breaking effect that causes explains all the quantum weirdness phenomena that we do in fact see. Now someone is going to obviously raise the point that slits aren't necessarily made of metal, therefore will not conduct electricity. But here's the thing. Man at CERN says at light frequencies even metals become dielectric. Even these glue sticks can be used as radio transmitters and receivers. If you tilt the slits forward or backward, you get a bending of the pattern. Okay, just in case anybody prefers to read it, I'll read it with me. So what you just saw, if you think about it, the only way insulators like glue sticks can be guiding photons to stay within the material, within the walls of it, is if there is electromagnetic induction at the surface, causing a Lenz's law type deflection of photons back towards the middle. So photons zigzag through like light through a fiber optic light pipe, fiber optic cable. So this implies some kind of skin effect of sorts, not exactly the same as the well-known skin effect in conductors where AC self-induction causes current to travel mostly down the outside part of a conductor, which is incidentally exploited in overhead high voltage power lines where the core is made of high tensile strength steel and only the outer part is of a good conductor such as aluminium. The skin effect in dielectrics, which includes metals at light frequencies, according to Fisk-Haspers of CERN, he says that above 300 terahertz they become lossy dielectric. It's clearly just local eddy currents which do not conduct along the length and merely keep the photons in check. So the skin effect in dielectrics is clearly just eddy currents, not conductive currents. They don't conduct along the length, they merely keep the photons in check. In other words, remember that Lenz's law is really just nature's way of keeping things in equilibrium, of trying to stop induction, resisting any relative change in the magnetism that would induce current. It doesn't just apply to conductive current though, it applies to eddy currents too. We only notice Lenz's law when we make a determined effort to generate useful amounts of electrical energy, because Lenz's law makes us put in all that effort. Unless you actually used a handheld generator or something, you're not likely to have noticed this, but trust me, it's Lenz's law. Very effective at making it hard work to generate useful amounts of electricity. So we only notice it when we make a determined effort to generate useful amounts of electrical energy, because Lenz's law makes us put in all that effort. The relative motion towards or away between the magnetism and the conductor in a generator, or the relative change in magnetism rising or falling in, say, a transformer, is what Lenz's law always opposes. In other words, it's not a mere mirroring of the magnetic polarity. That would give us free energy during the away motion of during the away motion phase of induction, because the mirroring of poles would be helping us when the away motion, and that would be giving us free energy. So that misconception is clearly wrong. It is the motion or change of magnetic field which is opposed, not necessarily the polarity. Obviously, during the towards phase of induction, this does imply that north meets north or south meets south. That's correct. Okay. Thank you for listening to me. How do I switch this thing on?